Hello, welcome everyone. It is a pleasure to have today as a colloquium speaker Arthur Kosowsky from the University of Pittsburgh. So let me start by saying that Arthur, back in the last millennium, at the end of the last millennium, saved my career. Therefore, the moment you get annoyed by my string of emails about scientific strategy and things like that, it's his fault. So Arthur has a PhD from the University of Chicago. Back when to get a PhD, you needed a single author paper under Mike Turner. And then he was a Society of Fellow at Harvard, which is a very interesting experience, apparently, and highly prestigious. Then he moved to Rutgers before being at the University of Pittsburgh. He's now a recovering department chair, and that's why he could take off some time and visiting us. He has also a lot of experience in editorial boards. So if you are puzzled about some of the things that happen in the editorials, he's also one of the experts on that. But let's talk about science. He has given us a very important contribution on theoretical cosmology, and in particular on understanding the physics of the cosmic microwave background and how we can learn information about physics from the cosmic microwave background. And if you've ever worked through the mathematics of the polarization of the cosmic microwave background, that's it. So if we remove that page from the history of or the book of cosmology, there's a lot of cosmology that we wouldn't be able to do today, including this experiment that go after the CMB polarization. He's also had a seminal contribution about the stochastic background of gravitational wave because that gives a signature in the CMB polarization. So it's all related. And finally, if any of you has ever run Markov Monte Carlo for interpreting CMB data, they go as fast as they go because of the Kosowsky variable, this change of variable that allow the MCMC to run fast and converge earlier, thanks to him. So, okay, so in terms of experiment, he's in the Atacama Cosmology Telescope. I believe you are the spokesperson of the Simons Observatory, or you are recovering from that too. And so without further ado, the floor is yours. Thank you.
Okay, thank you, Licia. I'm glad you started off with my biggest career accomplishment, which was hiring you. So it's been great to be here. As Licia said, I spent a lot of time over the last 7 years worrying about other people's careers. So it's nice to be here and be spending some time thinking about science again. I want to tell you about the Atacama Cosmology Telescope Act, which began as an effort it began as a proposal to the U.S. National Science Foundation in 2003. It was turned down, and we proposed it again the next year in 2004. And they said, well, actually, we're going to fund this other experiment called the South Pole Telescope, but we'll scrape together a little, you guys sound okay too, and we'll scrape together a little money to get you started. And so that money started in 2005. And we had a telescope in Chile by 2008 and started taking data and mapping very small bits of the sky and learning how to overcome all the challenges of doing this experiment. And we ran until 2022 when the telescope was decommissioned. And over the years, we had 2 different detector upgrades. We started running with the current set of with the final set of detectors in 2017, and they were fantastic. And we ended up making the largest area and highest resolution microwave sky maps that have ever been made from the ground. And so I will show you some of those maps and then tell you about what you do with them in order to get information out of them, and then some of the cosmology that we've gotten out of them. get this to work. There we go. Here's a picture of ACT on at the site in northern Chile in the Atacama Desert on the side of a mountain called Cerro Toco. The elevation is 5,200 meters, which is very high. It's high enough that you get really dumb when you go up there. So now, in the old days, we just toughed it out, but now everyone wears oxygen, so they're not quite as dumb as they used to be. ACT is inside this. This is a ground screen, and the telescope is right inside here. And then these are some of the class telescopes from another experiment. No, actually, these are another experiment called Polar Bear, which was at the same site. And this is not there anymore, although the base of the ground screen is. I just saw it for the first time last fall. And the site is now much larger and is being filled up with Simons Observatory, which is the next generation experiment. I'll show you a few pictures of that at the end. All right, so I will tell you about results mainly from this set of papers. This is a set of 3 papers about lensing of the microwave background, which we put out last year. And this is a set of 3 papers about the sky maps and the power spectra and constraints on cosmology that we put out 2 months ago. And then there are a few wrap-up papers, notably our paper on galaxy clusters, and then we've got a big paper about foreground modeling and a couple of other things that are going to come out as this year goes by. But we're getting to the end of ACT here. Well, okay. All right, so maps. Here is a plot of sky area that we cover at a certain depth. So the lower this number is, the less noise. You can think of this as the noise in the maps. This is, if you take a square arc minute of the map, what is the noise in microkelvin? And so you can see that in DR4, which was from about 2018, we were getting the deepest part of the sky, we were getting down at like 7 microkelvin, but that was only tens of square degrees. And then this noise just kind of took off. DR5, that was a data set that was released in, well, this was released in like 2021, and we were doing a whole lot better. And then this is the data set we've just released. This is the level of noise in the Planck maps. So Planck covers full sky at about this noise level, and you can see that now we have 18,000 square degrees of sky where we have noise that's better by factors of, well, 2 to 4 than the Planck sky maps. On this side, it's polarization, and we have similar sensitivity curves in polarization. Planck is up here, and the gap is even bigger in polarization. So here's one of the maps. Here's a section of one of our maps. We took data in 3 frequencies at 90 gigahertz, 150 gigahertz, and 220 gigahertz. This map is combining them so that red, green, blue scale, so that if you have a black body fluctuation, these combine to be gray. And so all the gray and white patterns you see in this map are black body. And then you see a bunch of other stuff. You see all these orange dots. Those are active galactic nuclei, which have a falling spectrum. They're brighter at lower frequencies, and so those look orange. Here is a big blue blob. That is a galaxy cluster, and that looks blue because the Sunyaev-Zeldovich effect suppresses the lowest frequency channel at 90 gigahertz and increases it so it makes the red channel less, so this ends up looking like blue. And then you can see it's hard to see here, but there's some sort of faint greenish blue stuff here. That's galactic dust. That's diffuse dust emission in the galaxy. So just really beautiful. Online, you can go to our website, and we have a map viewer where you can pan around this map and see all the stuff that's in it. It's really nice. Here is the same section of map plotted with red and blue is the intensity variation, and overlaid is the polarization of the map. The polarization is at a level that's about a factor of 10 lower in amplitude than the temperature variations. And so you actually can't see too much here in terms of correlations between the temperature and the polarization, because it's a fairly small correlation, but you can kind of look at it and say, wow, that looks really cool. And then we can take the polarization map and we divide it into, this is linear polarization. It's described with two Stokes parameters, Q and U, which are here and here. And then in cosmology, what we do is instead of Q and U, we go to a basis that's E and B, and you can think of E as the component of the linear polarization, which looks like a gradient pattern in a vector field, and B is the component that looks like a curl pattern in a vector field. And so here is the E polarization, and here's the B polarization. You can see that the B polarization is much smaller than the E polarization, and that's what we expect, because large-scale structure, which is the source of most of these perturbations in the maps, only couples to E mode polarization and not to B mode polarization. B mode polarization couples to other stuff, most notably gravitational wave perturbations, and so there's a big hunt on to find B mode polarization, and I'll talk a little bit more about that coming up. You can also take these maps and do you can filter them with a filter that's shaped like our beam. And so the thing that pops out is all the point sources. And so this is how we detect point sources in the map. Whoops. And you can see there's lots of point sources. Most of the point sources are either dusty galaxies or AGN. There's also localized sources, which are the galaxy clusters, and I'll say more about those. Those are not quite, most of them are not small enough to be true point sources, but still a filter like this does a good job of picking them up. And we have something like 30,000 point sources in our maps. So here is our entire sky area. You can see, so we have a strip that goes along the galactic plane, which, along the ecliptic plane, which gets most of the sky, and then down into the south, we have a lot of coverage because we're located at about, our latitude's about -20, so we can see a lot of the south. Our friendly competitors at the South Pole are down here, so they can get they have a deep patch that's something like this. You go to the South Pole because the atmosphere is better, you have less to fight against. However, you can't see that much of the sky from the South Pole because you're limited in how low to the horizon you can look. You don't want to look through too much atmosphere. And so in the end, they were ahead of us for a long time, but now that we learned how to map huge portions of the sky, this sky area overlaps with a huge number of things. Most notably, there's a big overlap with DESI, there's a big overlap with DES. It's essentially the entire sky area that LSST will cover, and so we have a huge amount of sky that we can cross-correlate with other surveys, which has turned out to be incredibly useful for getting science out of it. Here's the same map in polarization. You can see from the relative amplitudes that the polarization signal is a lot smaller. Okay, and here's a little animation that I think is really nice, showing the intensity map from ACT, our final intensity, on the top. And sorry, this is the E mode polarization on the top and the B mode polarization on the bottom. And on the left is ACT, and on the right is Planck, which up to this point has been considered sort of the state of the art of observing the microwave sky. And I'll just start this up, and you can see as we pan across the sky how much better become, compared to the Planck maps, this is essentially, these maps are entirely dominated by noise in Planck, the polarization maps, where we're seeing very clear signal in the ACT-E mode. To be fair, this isn't a completely fair comparison. Planck still does the best on the largest scale modes on the sky. The larger scale mode you go to, the more problems the atmosphere causes and the harder it is to separate out the signal from the atmosphere. So that's where Planck still has a big advantage over us. But what we do is we combine these together. So we have combined ACT and Planck maps, and we get the best of both worlds. This is Sigurd Nice, who's at the University of Oslo. He's our single point failure mode in ACT and SO, because he is the absolute master of taking enormous amounts of data, like 428 terabytes from ACT, and doing a maximum likelihood estimate saying, given this 428 terabytes of data with all the problems that you have in it and all the real world effects, what is our best estimate of what the microwave sky looks like that contributed to that signal plus noise? And so, yeah, if you happen to need to do that problem or something similar, Sigurd is your guy to talk to. All right. So here's the angular power spectrum of those maps. You take your map and you divide it into multiples by projecting it into components of spherical harmonics, and you get an angular power spectrum. So on this axis, this is the L index. So this is large scales here. This is small scales here. L of 200 corresponds to 1 degree on the sky, roughly. So this is 1 degree. This is a ½ degree. This is a 1/10 of a degree here. And on this axis is the power on that angular scale. And you see this typical wavy pattern here. We've appreciated for a long time that this power spectrum has a whole lot of information in it because it has all this structure in it. This structure is largely due to acoustic oscillations in the early universe. And so we understand what is the physics that makes all these bumps. And these bumps are well described by linear perturbation theory, so we can calculate these curves very accurately compared to measurements. And well, the first thing you notice is, damn, that's an amazing fit. I think this is one of the most impressive matches of theory and measurement that I've seen in all of science. I mean, it's an amazingly good fit to a very complicated spectrum. I like to ask my students, how, if you were describing this curve in a game where, you know, there's someone who's sitting with a piece of paper and you have to describe this curve to them, how much information do you have to give them before they can draw this curve pretty well? And you start thinking about how many peaks you have and their heights, and well, this in the middle, and what's it shaped like over here, and how is it dropping off, and over this whole scale, and you come up with, I don't know, 20, 25 pieces of information that you have to tell people. And these curves are from a 6-parameter model. And so there's a lot more information in this curve than in the model that's describing it. So an absolutely fantastic fit. The orange points are from Planck, and the blue points are from ACT. And you see there's this overlap region where they match beautifully. Planck is, we don't make estimates on the largest scales due to atmospheric noise, and we don't completely trust ourselves down here. And then at the smaller scales, we have Planck poops out because of the limit of its resolution. It's only got a 1.5 meter mirror compared to ACT, which has a 6-meter mirror. So we can go much further down in this tail. And the other thing that comes in here is there's a foreground model, and you have to use your multiple frequency channels and information about the spatial variability of the signal in order to separate this cosmological signal from the foregrounds. And the foregrounds actually become dominant somewhere around here. And so these curves actually go up like this, and we have to model all that before we can get down to this signal. But But you can really see the difference once we get to polarization. So here is E-mode polarization power spectrum, and you can see that Planck gets pretty ratty pretty quickly, and we have really nice measurements all the way down the damping tail, to the point where we can now make estimates of the cosmological model to high precision using only the polarization data, and then compare to the temperature data and essentially get 2 bites out of the apple. And I'm not ruining the story by telling you that they're completely consistent with each other. It's really remarkable. So in some sense, you can think of the line here going through the ACT points as a 0 parameter fit. You can fit this line using the temperature data, and then say, oh, well, let's just check and make sure that the polarization power spectrum also fits, and it does. And here is the cross correlation between temperature and E-mode polarization. Again, absolutely beautiful fit. So here's all of the 3 on the same plot. I also put in here the B-mode power spectrum, which is 0 for the primordial density perturbations. This line right here, it's not 0. This line actually comes from lensing. So the large-scale structure forms, it lenses the primordial polarized map and turns some of the E-mode polarization into B-mode polarization. We can calculate that very precisely. That's this line here. And you can see a number of different experiments are now filling in points on that curve, and that looks like it fits quite beautifully. And then finally, here is a curve for the primordial gravitational waves from inflation. This is the big prize that several groups have been chasing after for a long time now, with one false alarm so far, but we're still on the prowl for this. This is a really small, difficult signal, because we think the actual value or realistic value of this amplitude parameter R is not 0.1, in which case we would have seen it already, but it's more like 0.003, so down by a factor of 30 from this. You take this and move it down by a factor of 30, and you're way down here, and well, let's see, here's 1 order of magnitude, so you're down here somewhere, and we're trying to pull this signal apart from everything else, including the gravitational lensing signal, and it's really hard. So that's for the future that we're chasing after. And this is Thibault Louis in Paris, and he is our master power spectrum calculator, given the maps that Sigurd and company make. All right, so once you have that, what can you do with that? Well, the first thing that you do is say, let's see how well this constrains the standard cosmological model. Okay, so here is an example of the constraints from Planck. These are really good constraints, right? This is the baryon density of the universe. This is the inferred value of the Hubble parameter. This is the slope of the primordial power spectrum. This is the density of cold dark matter. And, you know, there's not a very big difference here. This is a scale where each one of these steps in the scale is a 1% change. So Planck is constraining omega BH squared to about 3% of something here. And if you combine Planck with ACT, or particularly with ACT, and then lensing information and BAO, baryon acoustic oscillation information from large-scale structure surveys, it shrinks this down by a factor of 2. And we're getting basically a 1% constraint on omega BH squared now. We're getting a 1% constraint on NS, and we're getting a 1% constraint on omega CH squared. And these have tightened up by about a factor of 2 from the Planck-only results. So when we say precision cosmology, this is what we mean. We can write down a model of cosmology that has 6 free parameters in it. It fits the power spectrum beautifully, and all those parameters are determined to essentially 1% precision. A truly great triumph of science. Yeah, so NS is moving over. This is actually of all the parameters to measure, it's NS is one of the tricky ones when you combine both sets of data, Planck and ACT, because as you saw, they are measuring different angular scales. And so if you have a small difference in a small systematic error in one of them, that NS is the thing that it most throws off. So would I bet my house that the value of NS has moved from here to here when you combine both sets of data? I'd say no. I'd probably bet my car, but my car is old and kind of crappy. So I think it's quite plausible that the value of NS is more like 0.975 than 0.965, but that remains to be seen if we've really settled on that value. Here's the list of all the parameters that we fit, so we sample these parameters and then we can derive all of these other parameters. And it does not list here a whole set of about 15 parameters that describe the foregrounds, and you have to model those simultaneously. But we still have vastly fewer parameters than we have degrees of freedom in the data, and so we can essentially determine most of the parameters of our foreground model also very precisely. And so people spend lots of time, like Licha, digging into the details of just how big should these numbers be, and how are they correlated with each other, and if you change this one, does that affect the other one? And it's become quite a sophisticated and quite a complicated game when you want to constrain lots of things at the same time. But you can do it with this quality of data. Here's an interesting plot. This is the curvature parameter of the universe, and Planck was preferring negative curvature values. When you combine Planck with ACT, so ACT, we actually prefer a value that's right at flat universe, right at no curvature. And when you combine them, you're still a little bit on the negative side, but the tail still includes 0. So that was kind of a funny anomaly in the Planck data that we suspect is probably was some issue with the Planck data on large angular scales, and I'm more confident about this one than about NS, that we're actually close to flat universe. And here is the lensing amplitude. Planck, these experiments can measure the amplitude of gravitational lensing because lensing smears out the power spectrum a little bit. It makes those peaks a little bit wider. And Planck had measured a substantial lensing amplitude from that, an amplitude that is larger than we expect from when you take the standard cosmological model and say, okay, that predicts the level of primordial perturbations. You evolve those forward and then just calculate how much lensing should you get. That's a lens of 1. And Planck was saying, well, from the fact that these peaks are a little bit wider, we think a lens should be 1.2. We're seeing 20% more of a lensing effect than we think there should be. We're not seeing that at all. We are seeing bang on a lens of 1. And we also confirm this by measuring not the power spectrum, but by measuring the actual lensing pattern. And I'll show you that a little bit. And we also get a lens of 1, so just the amount of lensing that the standard model predicts. So that's very nice. It looks like we're resolving some little funny anomalies that with the Planck determination of the standard cosmology. And here's also what I mentioned, that here's a bunch of different combinations of the data. So ACT-TT means the intensity power spectrum, the temperature power spectrum. ACT-EE means the E-mode power spectrum, the polarization power spectrum. And here's an estimate of these same cosmological parameters that I showed before. And you can see for many of them, we can compare the T and the E, and they're giving us the same number to a few percent accuracy. So I think that this is a fantastically amazing consistency check on what we're doing, that we really understand all the physics. This model that we have, this simple model, really does describe the universe, and everything is looking really beautifully consistent. Well, this is kind of a technical point. I think I'm going to skip that. All of our data and our code is available. So if you want to do cosmology, go to the ACT GitHub or the Simons Observatory GitHub site. All of the, let's see, I don't think all of the ACT data is there, but our ACT data is, all of our maps are available on NASA's Lambda site, which is the legacy archive for microwave background something, analysis or something. And you can get all of the data. Here you can get all of the codes that we have used to analyze the data. There's map making codes, there's power spectrum estimation codes. There are Jupyter notebooks demonstrating how to do various analyses. So you can go through and have fun and redo it all yourself and play with stuff and modify things to your heart's content. So please do this. Some of our competing experiments have not been very good at releasing their data in a form that the rest of us can deal with, and we want to set a good example here, so please make use of our data. Okay, so given how good our constraints on the standard cosmology are, we can now turn that around and say, okay, let's change standard cosmology. What can we change? And the answer is, well, we can't change things very much, or else you ruin the fit to those amazing power spectra. So we put out a paper last month. Erminia Calabrese is the first author, and Colin Hill was also sort of her co-leader of this effort, where they got together a whole group of ACT collaborators, lots of students, lots of postdocs, and sort of doled out various model extensions, changes to the standard model of cosmology, and then compared to the data and said, how much can we change how recombination works? How much can we put extra relativistic species in? All these different changes, and came up with the constraints on all these extensions of standard cosmology. So you can go there and look. The answer is that we don't see any preference for any particular extension of the standard cosmology compared to the standard model. So we cannot find a model where we say, oh, this one is definitely better. There are a few interesting constraints. This shows you how the game works. These plots are showing the difference in the temperature power spectrum that you get compared to the standard model, which is at 0 for various different modifications. So you say, well, I would like to put in axion dark matter. So let's say that 5% of the dark matter is in axions of 10 to the minus 26 eV. Okay, that seems like a crazy model to me, but what the heck? Let's calculate it and see what it gives you. And you can do those calculations, and you find that the temperature, the TE cross power, and the E mode and the E polarization power, those power spectra change by the amount shown in yellow. And the error band is in gray there. And so whenever anything in yellow peaks up above the gray, that's ruled out. And so for this case, we've picked a level of axion dark matter that's just enough that it peaks up above there. And so, oh, sorry, 5% of the dark matter cannot be in 10 to the minus 26 eV axions. Still could be 2%. So, so that's how this game works. These are all models that are allowed by Planck and ruled out by ACT. So we're gradually squeezing the vice and getting rid of various extensions. Some of these are quite interesting physically. Here's a couple of them. So relativistic degrees of freedom tell you, can I have a new particle species that was relativistic at early times beyond what's in the standard model? And so we can now rule out, for example, we can rule out having a spin 3/2 fermion that was relativistic before the epoch of primordial nucleosynthesis. And that is ruled out at 99% confidence level. So all you particle theorists, if you come up with some exciting new model that has a spin 3F fermion in it, if it was ever in thermal equilibrium in the early universe, sorry, your model's dead. Okay. We can rule out a spin 0 boson, which is actually the hardest one to rule out. That's now ruled out at a 94% confidence level. You know, okay, if that's in your model, okay, you can still give talks about it for another couple of years, but you know, we're working on it. The other thing that I wanted to show with extensions to standard model is lots of the extensions to the standard model right now are motivated by the fact that when you go out and you measure the Hubble parameter by looking at distant objects and figuring out how far away they are, the value that is most often talked about is about 74 kilometers per second per megaparsec from the Rees et al. Group. And then there's the Friedman group with numbers that are coming in a little bit less, and Licha and others have been doing a lot of work to try to bang their heads together and get them to come up with a consensus number and figure out what the problems are. But all of the direct measurements, well, most of the direct measurements are coming out higher than what you infer from the microwave background standard cosmology, which is a number of about 67. So if you think that, well, Adam Rees is right, I mean, hey, he won a Nobel Prize, so let's go with his number. That would indicate that there is actually a problem with the model, the cosmological model. Okay, if there's a problem with the cosmological model, how do we fix it? We know that the model has to be pretty darn close to the standard cosmology because I just showed you those amazing fits. So let's start putting in some other stuff. Okay, so there's been lots of stuff you can put in. You can put in early dark energy, a totally ugly, crazy idea, which says not only do we have dark energy at late times, but we're going to have a little bit of dark energy just around the time of recombination, and then it goes away. And not too much before recombination, because then everything goes. So, you know, a terrible model, right? But maybe that's the explanation. So let's calculate it. You can calculate it. And that actually will move H up a little bit, maybe from 67 is the Planck value, 68 here, up to maybe 70. You know, it moves it up a little bit. It doesn't move it up to here. But that's probably the best of these in terms of being able to move the value up. You can have a varying electron mass. Also a terrible idea, but hey, maybe. That moves it up a little bit. You can have a varying alpha. Also a terrible idea, but you know, why not? Move it up a little bit. These all move it up a little bit. If you change the number of effective degrees of freedom, oh, that's going in the opposite direction. Don't like that. This is, what is SIDR? Something dark, something. Dark radiation, yes, DR, dark radiation. Not only dark radiation, but self-interacting dark radiation. Hey, it moves it up, well, only a little bit. You're still within this band, okay. And at late times, you can change your dark energy model around, and that basically doesn't change. It's really hard to get an H0 of 74 and still be consistent with the measured microwave background power spectra. You're really in a straitjacket as far as H0 is concerned. If you can come up with a plausible model, not even based on physics, but just by randomly changing things in the standard cosmology that keeps consistency with the power spectra that I showed you and moves the inferred H0 up to 74, then quick write your PhD thesis paper about that, and you will get talk invitations from around the world to go talk about your new, you know, the blah, blah, blah model of cosmology where we just randomly change this thing and we get H0 of 74. Okay, that's a good homework exercise for everyone. Lots of people have been trying to do this. Not so much success so far. Yeah, that's what early dark energy was, right? It's saying, just imagine that you have this period of accelerating expansion right around, I mean, that's like the worst imaginary model you can make, right, from a physics perspective. Sure, but even with that, you're still not moving it up far enough. So yes, and those early dark energy papers have like 500 citations. So yeah, so that's your homework assignment. All right, let's talk about gravitational lensing for a few minutes. This is another very interesting thing that ACT at this point is leading the world in as of last year. So here's a cartoon of what happens if you put a mass in front of your microwave background fluctuations. So you put a mass in front, it bends the light coming to you, and you can see that it looks like it magnifies things in the center and then squishes them up in the outside. And so can we see this? Well, yes, because the pattern changes, right? Oh, if you look over here, there's a certain angular scale to this pattern of hot and cold spots. It's a Gaussian random field. It has a particular correlation length to it. Here, where it's being lensed, that correlation length gets larger. And so you're locally changing the power spectrum of the Gaussian random field due to lensing. So that idea allows you to look at your maps and say, okay, let's say that we have a Gaussian random lensing field, which is magnifying it in some places and contracting it in other places. And let's estimate the size of that field that is changing the size of the perturbation. So it's a second order effect. It's a quadratic effect. And Hu and Okamoto in 2003 first wrote down the formalism pointing out that, yes, you can do this. And here's how you estimate the statistics of that expanding and contracting modulation field. And that is a direct measure of the mass density in your lenses. And it measures all the mass from us to the last scattering surface. So you're getting a weighted average of all the mass all the mass fluctuations along a certain line of sight. So I think I have a picture of so here is how the lensing signal depends on redshift. So if you look at only the mass that's below, say, a half, you get this much lensing power. And then if you go all the way up to all the mass out to 20, which is going to be all of it, then you get this total curve. And we can actually probe these different levels, not by the total signal's right here. And so I'll show you some measurements of that. But we can also dig into this by correlating our lensing maps with large scale structures. So you say, okay, here's a survey of galaxies that goes out to 0.5, and I cross correlate that with our lensing map, and then we can see how much of our lensing map is coming from that part of the redshift distribution. So that's an entirely other game that I'm not going to have time to talk about. But for the total lensing signal, here is our lensing maps. So you can see over the same area of sky covered, okay, here's hot spots and cold spots. Those are not hot spots and cold spots in the intensity. These are hot spots and cold spots in the amount of magnification or demagnification that are in the maps. And so this is our best estimate of the lensing map. This is a total the statistical weight of this detection is now past 60 sigma. So we're really measuring this. And we can tell that we're getting the answer right because of this amazing map. In the background, in white and black, is this lensing map that we produce showing the total amount of projected mass. And overlaid on the top are contours of the cosmic infrared background map. So if you look in infrared light, there's another background of radiation. It's not like the cosmic microwave background, which is primordial. This is not primordial. It's coming from young stars. They put out lots of radiation, then it gets redshifted into the infrared, and we see it today. And if you model all the starlight, the cosmic infrared background, the most contribution from that is from around redshifts of 2. And that is a fantastic coincidence because that is the redshift at which also we're most sensitive to microwave background lensing. Because for lensing, you get the most effect when you're about halfway between your source and your lens, and a redshift 2 is halfway between us and a redshift of 1,000. So these two things are essentially tracing the same population, and you can see that they're almost the same map. They're beautiful. I mean, where we have the most lensing magnification, we also have the most cosmic infrared background. And this hasn't been filtered or anything. This is just slapping the two maps on top of each other. And I remember my jaw kind of dropping open when I saw this. It's just incredible how well they match. So we really are seeing the mass distribution around that's peaked around the redshifts where the infrared background is coming from. Yeah. So that's quite remarkable and gives us faith that we're not only modeling the early universe correctly, but we're seeing the late universe correctly also in the microwave background. These are scales at which the dominant contribution to the lensing is coming from linear or almost linear matter perturbations. It's on large scales, not from individual galaxies, it's from big variations in the matter field over the scales that are larger than any bound object. So super duper clusters, the Great Wall, bigger than that, hundreds of megaparsec size up to gigaparsecs in size. And we're getting those bang on to what the standard cosmology predicts from the perturbations at the last scattering surface. Here is the lensing power spectrum. So these points are measurements of our latest measurements of the lensing power spectrum that I just showed you. And the black is the best fit to the best fit cosmology model based on the Planck the final Planck data, which is essentially the same as the one from Planck plus ACT. And so this is a 0 parameter fit to these points. And you know, it's right there. We actually did the analysis of the lensing blind, and we had a telecon where we unblinded, and everyone's sort of sitting there nervously waiting because, you know, this looked a little funny, and there's this bump here, and we had disguised the data, and so no one knew how well this was going to fit, and then it just bang on an amazing agreement. So if you say, what does that lensing tell us? That lensing constraint restricts cosmology to be in a one-dimensional subset of the space of this is a measurement of the amplitude of matter perturbations. This is the matter density in the universe. This is the Hubble parameter, and you have to live in a one-dimensional line in this space. So it's really quite constraining, and then you can use this to compare with all sorts of other local measures of the mass distribution and get lots of interesting inferences about the local structure out of it. Let's see. I think I'm going to skip ahead here. Here is the one other really interesting inference that's coming from lensing, and that is that the shape of the lensing power spectrum is sensitive to neutrino mass. And the reason is because there are lots of neutrinos in the universe. We have a cosmic neutrino background in the same way that we have a cosmic microwave background. The neutrinos decoupled thermally at earlier times, so the temperature of the neutrino background is lower by a factor of 4/11 to the 1/3, which is always a favorite homework problem in graduate cosmology. So it's at a temperature of about 2 Kelvin instead of 3 point whatever it is. But we think the neutrinos are there. They're very hard to detect directly. But if the neutrinos each have a very small mass, that adds up to a large amount of mass in the universe. Neutrinos are light enough that they do not easily get bound into structures. Rather, they're streaming along, and if they're streaming along and have mass, they tend to gravitationally smear out small-scale structures. And we are sensitive to that. If you get rid of some of the small scales, that will bend your lensing power spectrum over at small scales. And so we can measure that and see how much bending over is there and construct this plot. So this is our probability distribution for the sum of the three neutrino masses. In order to be consistent with solar neutrino oscillations and atmospheric neutrino oscillations, the minimum amount of neutrino mass that you can have is about 0.057 eV. It's 0.056, something like that. That's if your lowest neutrino mass eigenstate is 0, and then the smallest splitting is the next one, and the big splitting is the next one after that. That gives you a total neutrino mass of about 0.056, which is right here, this one. And here is our probability density. So, you know, we can still live with that, although we're not seeing a peak here yet. And so, you know, we're starting to really put pressure on that. Here is the inverted ordering, where your lowest neutrino mass state is 0, and then the big difference is first, and the small difference is second. That gives you about 0.11, 0.11 electron volts. That is now ruled out at 99% by our data, taken at face value. Would I bet my house on that? No, but I would bet my cheap car on that. Okay. So this is really interesting. We've gotten here faster than I thought we would. About 3 years ago, I was talking to some of our neutrino experimenters at Pittsburgh about, hey, you know, I think we're going to beat you guys to constraints on neutrino masses. And they were like, no, they couldn't believe it. And I started telling them about this, and yeah, they thought that was kind of interesting, and went off and started working harder, got a little nervous. And I think we have beaten them to ruling out at least the inverse hierarchy of neutrino masses. Let's see, how much time do we have here? We got about 5 minutes. Let me put in a plug for galaxy clusters. Galaxy clusters, really interesting. They're the biggest bound objects in the universe. And all of you particle physicists might say, well, you know, who cares about that? That sounds like some messy astronomy. And there is a lot of messy astronomy about galaxy clusters, but galaxy clusters are also great for physics, because to a physicist, a galaxy cluster is a big bound blob of dark matter and some thermal equilibrium gas in it in gravitational equilibrium. Oh yeah, and then by the way, there's some galaxies sprinkled in there too, but you know, it's just a big object. And the distribution of size of those objects depends very sensitively on your cosmological model. If you say, given a Gaussian random field of initial perturbations, what is the mass spectrum of clusters we should have today? The ones at the high mass end are exponentially suppressed. And so therefore you can look at the high mass galaxy clusters in particular, and that is how many of those there are above a certain mass threshold is a very sensitive probe of your cosmological model and your expansion history and the statistics of your initial perturbations. Here is our map of what's called the Compton Y parameter. This is a particular spectral distortion which is due to hot gas, and galaxy clusters have hot gas in them just due to adiabatic compression of this gas in the potential well. And so you can take this map and find all the objects in it. And so here's an example of one of them. This is like we saw before, where you have this blue spot in your intensity map. That's what it looks like in intensity. This is what it looks like in the Compton Y map, where we've decomposed those 3 frequency channels into one of them a component of this Y distortion. And then if you go to this point in the sky and look with an optical telescope, you see this, and it's like, oh, yep, there's a whole lot of galaxy clusters, a whole lot of galaxies there in the spot in the sky where we see this. So here is our
most recent published result from DR5 from 2021, this map has 4,000 galaxy clusters in it. We're getting ready to publish a new paper where here's the sneak preview. We have almost 10,000 clusters with signal noise greater than 4 and measured redshifts for all of them. We have over 1,000 clusters at a redshift greater than 1. We have 120 clusters of redshift greater than 1.5. The highest redshift cluster is right below redshift of 2. This is vastly more clusters than anyone has ever put together in a cluster catalog before. Planck had about 1,000, 1,200, but Planck's resolution isn't as good as ours, and so a lot of these clusters just get smeared out. They only see the biggest ones. And this is a lot bigger than X-ray selected cluster catalogs, because the X-ray signal drops off super fast with redshift. Everything just gets too faint and you only see the nearby ones. Whereas we see all of them, we think. And so here's a plot of cluster mass here versus redshift here and where all the clusters are. And you can see this is an optical survey. So the optical surveys are only seeing the lower mass clusters and only out to about a redshift of 0.8, and then there's just this cutoff. And you just can't see anything much beyond that. Whereas we think all of the clusters that exist in the universe above a given mass threshold. So that is a very useful, beautifully selected sample for then doing analysis to decide, is this consistent with the standard cosmology or not? All right. Here is the ACT being hauled off to its old telescope retirement home, which is another spot in the desert not too far away. And let me just show you a few pictures to close here of what's coming up next, which is Science Observatory. So here's a picture of the same site, ACT. It was right here in this ground screen. So right next to it is this big complex. And we have, this is the new ACT right here called the Large Aperture Telescope. Here's 3 other small aperture telescopes. These are similar to the BICEP telescope that's at the South Pole. These are the ones that are designed to look for the B-mode polarization at large angular scales and look for the signature of inflation. This is going to do similar science to what I just showed you, but at higher precision and higher signal to noise ratio. Here's what a small aperture telescope looks like. The light comes in here. This is a ground shield. The light comes in here. It's actually a refracting telescope. It's a lens that's about 1 meter in diameter is the primary lens, and the detectors are down in the bottom. This is what the business end of it looks like. This is where the detector arrays are. And here is the Large Aperture Telescope. This thing is as big as about a 3-story house. You can see the stairs going up here. It's on a huge turntable, so the whole structure goes back and forth like this about once every 10 seconds. It's quite remarkable to see. The primary and the secondary, which are each 6 meters, are in here, and the telescope points by this whole thing rotates like this way. And so you look at some elevation and then the whole thing goes back and forth like this to scan. And then you maybe go to another elevation and go back and forth like this. And you do that a whole lot and eventually make maps as the Earth rotates and the sky passes over the telescope. This is the inside of the Large Aperture Telescope with me standing in front of the cryostat. This cryostat this is the back of the detector plane. These detectors are cooled to 0.1 Kelvin, so 100 millikelvin. And all of my condensed matter physicists, they say, oh, what do you cool to? And I say, 100 millikelvin. They're like, we get down to 100 microkelvin. And I said, yeah, but you can't stand up inside of your cryostat. I mean, this thing is huge. And this is one of the dilution refrigerator, helium-3 dilution refrigerators that cools this part down that cold. So that's now closed up and operating. We're operating with 30,000 detectors compared to ACT's 3,000. And there's going to be an upgrade, assuming that the U.S. National Science Foundation actually does start spending money again and doesn't decide to cancel our project over who knows what. And we are planning to fill in the rest of the space that we have in here. The detector plane can have about twice as many detectors as we currently have in there. So we'll end up with about 65,000 detectors in the fully filled focal plane, and then another 65,000 distributed between 6 small aperture telescopes is the current plan. So that's all happening. We are now taking data with all 4 of those telescopes. We should add 3 more sats and fill detector plane within the next 3 years, and forge our way to even more exciting constraints on cosmology than I've been able to show you today. So that's all I have for you, and I'll be around for the next week, so please come by and talk about cosmology. Thanks very much.